A professional receives an email declining a meeting. To respond, they open an AI assistant and type, "Write a 2-sentence reply." This is a task requiring perhaps 30 seconds of unassisted cognitive effort. The model obliges instantly. The text is copied, and the user moves on. This specific, routine transaction represents a structural shift in the boundary between human and artificial cognition. Today, we are engineering artificial systems to process millions of variables simultaneously, while our biological capacity for sustained attention is empirically contracting. To accurately map this expanding gap, researchers translated human working memory and AI context windows into a common mathematical unit, token equivalence. The resulting asymmetry between machine capability and human processing span is defined as the cognitive divergence. This divergence creates the conditions for a theorized feedback loop, a cycle where machine growth and biological change may begin to reinforce one another. The modern era of language models began in 2017 with the transformer architecture. It introduced a self-attention mechanism that computes representations by attending to every single pair of input tokens simultaneously. This mechanism imposed a strict quadratic bottleneck, O of n squared. Doubling text quadruples computing power, capping early models at a 512 token limit due to GPU constraints. Flash attention rewrote the code to tile matrix operations into shared memory, bypassing the physical limit and creating an efficient linear cost. With the hardware limit removed, AI context windows entered an exponential growth rate, specifically tracking a mathematical lambda value of 0.59 per year. That translates to a doubling time of roughly 14 months. Today, frontier models handle up to 2 million tokens in a single prompt. AI context scaling now follows algorithmic efficiency rather than the physical memory limits of the chip, allowing for nearly unbounded workspace growth. The human biological equivalent of an AI context window is the episodic buffer, the limited capacity workspace in your working memory where incoming information is actively held, integrated, and processed. Between 2004 and 2020, longitudinal observational research tracked the screen focus episodes of knowledge workers using precise application logging software. In 2004, the baseline measurement for a single continuous screen focus episode was 150 seconds. By 2020, that number had stabilized at a modern equilibrium plateau of 47 seconds. Researchers calculated the effective context span to convert biological limits into machine tokens. It multiplies session duration, a reading rate of 5.28 tokens per second, and a comprehension scaling factor. In 2004, deep focus earned a 2.0 factor. Today's fragmented switching drops this integration factor to 1.2. This lack of deep integration means that by 2026, the human effective context span drops from a 16,000 token baseline down to just 1,800 tokens. The human cognitive workspace is not merely stagnant, it is actively shrinking and compressing under our current digital platform conditions. This chart plots the cognitive divergence, the exponential growth of AI context capacity in blue against the steady decline of human effective context span in red. The exact point of intersection occurred in November 2022 with the launch of ChatGPT. Raw capacity, however, does not equal perfect recall. Large language models suffer from a retrieval degradation phenomenon known as context rot. Because of a mathematical property called rotary positional embedding decay, models systematically decrease their attention weights on mid-context information. They remember the beginning and the end of a document perfectly, while accuracy drops steeply in the middle. If we aggressively penalize the models for this architectural flaw, their effective functional span drops from 2 million tokens down to a quality-adjusted range of 100 to 200,000 tokens. Even after applying this heavy quality adjustment, the capability gap leaves us with a staggering 100 to 1 asymmetry in processing power. This 100 to 1 processing gap drives a specific behavioral phenomenon, the delegation feedback loop. As AI systems become highly capable and frictionless to use, the cognitive threshold at which humans delegate tasks drops. Offloading tasks within your biological capacity results in reduced cognitive practice, bypassing the effort required to actually do the work. Cognitive load theory defines this specific internal effort as germane cognitive load, the necessary neurological work required for schema construction and long-term skill maintenance. Without that daily friction, neural substrates responsible for sustained attention, like the prefrontal cortex, lack the stimulus to maintain fitness, leading to attenuated capacity. Direct EEG evidence shows that users completing writing tasks with AI assistance exhibit measurably lower cognitive engagement signatures, accumulating what researchers term a cognitive debt. Because genuine capacity has decreased, even more tasks exceed the user's lowered threshold, forcing further delegation. Persistent cognitive outsourcing rewires the brain's workspace, guaranteeing the divergence widens. This dynamic fractures the industry-standard human-in-the-loop oversight model heavily relied upon for AI safety. You cannot have a human meaningfully review a model's million-token context when the human biological processing limit is effectively 1,800 tokens. This creates a structural failure defined as a state of asymmetric epistemic access. Traditional verification becomes biologically impossible when the human capacity to review the context has been engineered completely out of the loop. We are now fully reliant on artificial systems whose complex syntheses we simply lack the neurological endurance to independently verify. This shift changes the very nature of how we